group, do not leave before telling me which group you have formulated, because we all forgot, including myself, to remind you that before leaving lab on Wednesday you should have formulated your group of 5, because you need to know which group you are in, because next week not everybody's going to be working on the same thing. So you need to know which pre-lab quiz you're going to prepare and what lab you want to prepare. So please stay a few minutes after class and come up to me with a group formulated of 5. We're going to be 20 students in Wednesday lab, each group 5. Do not form a group of 3 or 4. Make sure your group has 5. Okay, so let's get going with things. Okay, recap questions. Before we do that, I just want to remind you guys that participation points count when you ask questions as well, not just answer. It's very important that you ask. Sometimes you can ask me to repeat something, to clarify something. It's okay. There's no stupid questions. All questions are good questions and need to be asked. So please do so. Sometimes I get carried away. Since I know the material, I assume that you understood it, but that doesn't mean that you did, so interrupt me. Okay, let's name a few examples of adsorption chromatography. Ray? No, okay, let me clarify. Different modes of separation that are also adsorptive chromatography, not the stationary phase or mobile phase. Different modes of separation, Erica? What's that? Affinity? Yes, affinity chromatography is an adsorption chromatography. What else? You didn't raise your hand, sorry. Sven, huh? Ion exchange? Do you have anything else? Size exclusion. Is it adsorptive chromatography? What type of interactions are there in size exclusion chromatography? What is, okay, you put yourself in trouble. Size exclusion, what's the separation based on what? Very good. So it is physical. You don't have molecular interactions. So you don't have adsorption to the stationary phase. Stationary phase is just a merely inert phase with particle pore sizes. So they go in and out. There's no interaction. So it's not adsorptive chromatography. I saw Agnes' hand up for adsorption chromatography. You put your hand up for something, didn't you? No? Okay, never mind. Delayed response from me. So you said affinity chromatography, ion exchange chromatography, hydrophobic interaction chromatography. These are all specific forms of adsorption chromatography. But you can have a general form which is based on, if you have silica, for example, an interaction would be based on polarity. So this is not really very specific type of adsorption chromatography. So what molecular weight interactions between solute and stationary phase are involved? We already said nothing for size exclusion. Ion exchange? Yeah, go ahead. Electrostatic interactions? Hick? Yeah? Go. Size exclusion, we established that, yes, nothing. What about hydrophobic interaction chromatography? Hydrophobic interaction. Affinity chromatography? Yes, Farah? All of them, that means what are they? Hydrogen, but no covalent. If you have a covalent interaction, they're never going to leave this column. They're going to live there and stay there. Okay. What is the difference between cation and anion exchange chromatography? Go ahead, Josie. Positively charged groups attached to the stationary phase? Who agrees with Josie? Look, you don't have supporters in the room. Why? She's very nice and sweet. But,
In order for cation exchange to occur, you have to have negatively charged
yeah,
molecules on the stationary phase.
yeah,
Free up.
right. So cation exchange chromatography, you're exchanging cations. So your sectionary phase has anions on it. And the opposite is true for anions. So you're exchanging ions that are negatively charged, and your stationary phase would have a positive charge. Okay, how do you increase the mobile reverse phase chromatography? How do you increase the strength of the mobile phase? What do you do to it? Well, let's see. You guys are good in participation. Uh, in reverse phase. In reverse phase, do you increase polarity? You, you make it more nonpolar, because in reverse phase your stationary phase is nonpolar, sorry, and your mobile phase starts off with more polar. And then if you want to attract those nonpolar molecules that are interacting with your stationary phase, you increase organic phase percentage in your mobile phase. What about hydrophobic interaction chromatography? How do you increase the strength of that mobile phase? Okay, so what's the basis of hydrophobic interaction chromatography? You remember? You do have function groups that are hydrophobic, yes, but how do you make your components interact with your column? What do you put them in? What do you start your mobile phase with? Yes, so you start with a high salt concentration, and now they're interacting with your column. They're precipitated on your column. How do you get them out? Yes. Yes, so that you reduce the salt concentration, so now they're more liking your mobile phase, so they leave the column. In affinity chromatography, how do you increase? Yes, Sven? Huh? Changing the pH could be one, yes. If you want to do a very specific um, type of changing the mobile phase, what would you do? If you have a ligand, yeah. Go with it and interact less with the column, because now the ligand in your mobile phase is competing with the ligand on your stationary phase. So yes, perfect. What is the order of elution in hydrophobic interaction chromatography? So if you have a mixture of proteins, some are more hydrophobic than others, what's the order of elution? What will elute first? So remember that compounds are interacting with the column. And the stronger the interaction, the more they're going to stay on your stationary phase. So what will elute first? Less hydrophobic. So the more polar will elute first. Okay. What about ion exchange? Yes, Ben. Yes. And then, depending on their ionic valence, so the ones with the highest ion valence will stay longer on the column, and the ones with the lowest ionic valence will leave first. Size exclusion. Emily? Yes. Yes. Okay. Very good. So the smallest one will have access to all the pores within your particles in the column. The large one will not have access to the pores, so they will move with the mobile phase between the particles and elute. Okay, very good. So review these concepts, review this table. It just gives you a very good idea about the different types. Like I said last time, it kind of a great summary for chromatography in general. Okay, so what I want to do now, instead of just moving forward with this, talking about separation of different compounds and how we get resolution, I want to jump ahead and talk a little bit about what you're going to do in the lab so that I don't run out of time at the end of the lecture. So this is actually a request from Cindy, because oftentimes we don't get to HPLC lectures and GC lectures before you get to the lab. So you want to have some kind of an introduction to what you're going to do in the lab, because we're finishing up basic chromatography, and next week we have 2 lectures on HPLC and 2 lectures on GC. So what I'm going to review with you quickly is what we're doing in the lab. So next week is your first rotational lab, so yay, we started the real experiments. So 2 groups on Monday, A and B, will be doing the HPLC lab. So Monday lab has already formulated groups, so you know who your group is. So make sure you complete pre-lab questions regarding HPLC. Group C for Monday will be doing GC lab. And then the Wednesday group, D and E will be doing HPLC, and F and G will be doing GC. Wednesday group, write this down, and then at the end of the lecture, you can select which group you're going to be in and decide which one you're going to do. So at the HPLC lab, we're going to use a reverse phase chromatography lab, where we use a stationary column that is a nonpolar and mobile phase that starts as polar, to separate caffeine, separate and quantitate caffeine in different beverages. So you're going to have 5 different beverages that vary in the caffeine level. Each beverage will be prepared differently in different dilutions, and there will be standard curves prepared for you. Not standard curves, standards ran for you, and you will prepare the standard curve. And you're going to estimate how much caffeine you have in all the different samples and compare those to reported literature. GC analysis is going to be a really interesting lab. It involves more sample prep than the HPLC lab. So the GC lab involves that you get different oils, and this is really fun lab because we don't tell you what the oils are. So there's going to be some guessing, and there is an adulterated oil that we mix 2 different oils together. So you have to guess what the adulterated oil is, a mixture of what. So you're going oil. Basically, in order to identify the oils, you need to determine the composition of their fatty acids. So fatty acids are not volatile and not thermally stable. So what you're going to do, you're going to saponify your oil, basically. Let me go down here a little bit. So you're going to saponify the oil to produce fatty acids, to break the oil into fatty acids. And the fatty acids, you're going to derivatize them into fatty acid methyl esters. So you're going to make them thermally stable and volatile. So it's a chemical reaction, and we'll go over it in the lab with you. And then your lead TA is going to be Chelsea, and the lead TA for HPLC is Amy, and the brave soul is Claire, that helps with everything. Okay, so you're going to prepare FAME, and then you're going to separate the different fatty acids using GC, and you're going to get a profile, percentages of the different fatty acids. And then based on that, you review literature, and you say, oh, this is corn oil. This is olive oil. This is nothing. It's an adulterated oil, but what 2 oils were mixed together. So it's really fun and kind of like a puzzle that you're going to kind of solve. So these are the 2 labs. This involves minor sample prep, and we're going to go over the HPLC system and how to analyze spectra and all of that. And this is involving more of a sample prep. So, but what I want to do right now in class is show you YouTube videos, which are posted on the web. But if I show them to you now, you have no excuse not to know what HPLC and GC are. If I leave them on Moodle, some of you will watch them, some of you won't. So, but But the only problem is my audio is not connecting to the room's audio. There must be something faulty. But what I'll do is I raise the volume to the highest. And this is an HPLC 1. It's tricky.
High-performance liquid chromatography, or HPLC as it is commonly known, is an important analytical technique used to gain both quantitative and qualitative data for samples produced in a variety of industries, such as pharmaceuticals, food products, and industrial chemicals. The purpose of this guide is to consider this question: what is a HPLC instrument? We will focus on analytical applications. The implementation of HPLC requires the use of precision instruments. There are two main reasons for this. The first is that sophisticated instrumentation is needed to create suitable method conditions, and the second is that reproducible control of these conditions is critical. A HPLC system can at first glance appear daunting to the new operator. A full understanding of the components common to all HPLCs can transform bewilderment regarding a complicated arrangement of tubing and electronics into an appreciation of a logical and well-designed piece of analytical equipment. At the heart of all HPLC systems is the column. This is where the separation of the components of interest in your sample actually takes place. It is the interaction of the stationary phase contained in the column, the mobile phase, and the sample components, which forms the basis of this analytical technique. The stationary phase in your column is typically, but not always, in the form of very small spherical particles. The diameter of these particles is in the order of a few microns. That's 1/1000th of a millimeter. In analytical HPLC, the particle size diameter ranges from approximately 1.5 to 10 microns. To achieve a separation, we need to create a flow of mobile phase through the column. To enable this, tubing is connected to the ends of the column. The very small size of the particles means that a flow of liquid needs to be pushed through under high pressure to get a reasonable flow rate. As a consequence, the tubing needs to be connected in such a way so as to withstand the high pressure. This is achieved by the use of compression fittings. These fittings screw securely into the ends of the column to create a leak-free connection. So far, we have a HPLC column connected by tubing and compression fittings to the mobile phase reservoir. We will add a vessel to collect the waste at the other end of the column. To keep the mobile phase moving through the column at a steady flow rate under pressure, we need to introduce a pump in the flow path. This instrument is designed to draw the mobile phase from its reservoir and deliver it to the column at the required flow rate. Now we have a flow of mobile phase through our stationary phase, but we need a way to introduce the sample for analysis. For this, an injector is required. This instrument is designed to inject a small aliquot of sample, typically in the order of a few microliters, into the flow path of the mobile phase prior to the column. It has to do this without altering or stopping the flow of the mobile phase, and thus maintaining the system pressure. In most modern systems, this process is automated, and samples are placed in vials which can be injected by the autosampler in the order and amounts programmed by the operator. When the sample has been injected and passes through the column, the separated components need to be detected in some way so as to convert the results of the analysis into useful data. The detector is designed to be able to recognize some characteristic of the sample component. The most common detector is probably an ultraviolet or UV detector. This works by passing a beam of UV light through the flow path of the mobile phase, measuring the absorbance. For those components which absorb UV light, the response obtained will be proportional to the amount of the component present. Not all components absorb UV light, and those that do have different responses, so these factors need to be considered when choosing a suitable detector. There are a range of different detectors available, which may be used for HPLC. These include MS, which passes the flow coming out of the column into a mass spectrometer, thus obtaining information on the amount and molecular weight of the compound. Other detectors which you may have encountered include evaporative light scattering, charged aerosol, fluorescence, and conductivity detection. Some kind of processor is required to convert the responses from the detector into usable data. Purpose-designed software applications called chromatography data systems are available. Common examples are mPower, Clarity, Chromalion, and EasyChrome. In gradient analysis, the composition of the mobile phase is changed during the course of the analysis. To enable this, we need another mobile phase reservoir and some way of mixing the two. The mixing may be performed before the pump, as shown here, in which case it is not yet under pressure and is called low pressure mixing. Or the mixing may be performed after the mobile phase flows through the pump, in which case it is under pressure and two pumps will be required. Systems which use high pressure mixing are often referred to as binary systems, since two pumps are needed. In practice, low pressure mixing with a proportioning valve before a single pump is most commonly used. Another instrument which is typically included in a HPLC system is a vacuum degasser, since all air needs to be removed from the mobile phase for optimum performance. Temperature is an important method parameter which needs to be controlled in HPLC analysis. For this reason, the column is often housed in a compartment which can be temperature controlled. Many HPLC systems have the capability to mix 4 mobile phases. These are known as quaternary systems. So what happens during an analysis? The mobile phase is flowing through the system from the mobile phase reservoir to waste. We will inject a mixture of 3 components, shown here using 3 colours, pink, green and blue. At the head of the column, when the sample first encounters the stationary phase, we have a mixture of all 3 components. The equilibrium between each component, the stationary phase and the mobile phase is different for the 3 colours in the mixture. In our mixture, the pink component spends more time in the mobile phase relative to the green and the blue and travels through the column quickest. The blue component, however, spends more time on the stationary phase relative to the other 2 and travels through the column slowest. As the mixture passes through the column, they become more and more separated. The pink components leave the column first, and on passing through the detector, a peak is observed on the processor. Then the green component passes through the detector, resulting in another peak, and finally the blue component passes through and has a corresponding peak. This plot of the separated peaks is referred to as a chromatogram. Overall, the blue component spends more time in the flow path and has more time to spread out. This results in a broader peak relative to a component which is passed through in a quicker time, such as the pink in this example. It depends on the actual method parameters being used, whether this band broadening effect is as noticeable as it is in this example, where you can see that the peaks are progressively broader as time passes. Now that we have looked at the individual components of a typical HPLC instrument, you should be able to look at the system that you use in your laboratory and understand how it works. This video is provided as an example of the training resources available from Moore Training Services. Visit the website for more information on our training solutions for pharmaceuticals.
Okay, no advertisement. Okay, so now we'll do the GC, but the GC video has music rather than somebody's talking. So I'll be doing the talking. I hope I do it correctly, and Chelsea will correct me if I mess it up. What? Okay. So I'm going to reduce the volume. Or keep it's a calming music, so it might put you to sleep. So I'm just going to reduce the music. And go here and play. So you have a box. So it is a gas chromatography box. And yeah, so it's an oven. And in the oven, you have your column. And like we said earlier, the GC columns are long capillary tubes made of glass, but very thin, and they coil. And then you have an inert carrier gas, usually it's helium, and then you have an injector. They're going too fast for me. Injecting the sample, going through the column, interacting with the column, and then there's a detector. And then the signal is amplified, and then it's detected. You get a chromatogram. I think, I don't know if they're going to go into more detail, but let's see. Ah, now they're slowing down. The injector, so usually in GC you only need a very small volume of the sample because your column is very small and then it's a capillary. So there is, the sample goes in with the carrier gas and then there is a separation where a split outlet, some of the sample will just go out and very small amount will go to the column. Most of the sample will go out and some very small amount will go to the column. Okay, got that? Reinforcing what I'm saying. Oh, well now the sample got injected. And most of it is going out and then a small portion is coming to the column. So the column is mostly made of glass tubing, very thin. On the interior side, you have a thin layer. It's capillary, so you have a thin layer of your stationary phase. When we talk about resolution, this helps a lot with improving resolution because it reduces equilibrium time. Then your sample, again, 3 components. Some of them is spending more time on the stationary phase. Some is moving more with the mobile phase, which is gas, due to their size, polarity, as well as thermal evaporation temperature, because you will be building gradient with temperature changes. So so the blue one comes out first, the red, and then the green. The longer the column, the better separation you will get. Okay, so it goes to the detector. I think in this example it is flame ionization detector. So basically what happens is you generate a flame by having oxygen source and hydrogen. So it's a hydrogen flame. So the samples are coming in and they get burnt by the flame. There's an igniter here. So you have air, hydrogen, the flame is generated eventually, and the sample gets burned. And then a current is passed over the flame, and the electron, because it's flame ionization detector, they will have different current based on their composition. Mostly carbon and hydrogen compounds are detected the most using F5. And you can see peaks are very small, you get very good separation, and you're going to see something very similar for the different fatty acids separation. Give you relative abundance here. Again, advertisement. You can click, exit, goodbye. Okay, so there you are. If you want to have a popcorn movie night tonight or Sunday, you can watch these again. No, you're done. Okay. Friday night, yes. With beer. Where is it? Okay, so I'm going to go back. We have 20 minutes. Let's see what we can do here. Okay. All right, so now that you have learned the different types of chromatography, you have liquid chromatography, gas chromatography, supercritical, fluid chromatography, and also you learned about the different modes of separation. Ion exchange, cation, anion, etc., hydrophobic interaction chromatography. So now you have a solution and in it you have components that you have extracted from a certain food product. And we'll give examples during the semester as we cover different chapters. So, and then now you have to separate, make sure the components within your sample are resolved, meaning separated from each other, so that you can detect them. First of all, identify what they are, and then quantify them. So, when you start thinking about developing a separation, so you have two compounds eluting or co-eluting together. You want to make sure that there are two separate peaks like that, and then so that you can identify them correctly and quantify them. So the first step that you would do or try to do is, okay, what does your lab have? Do we have standard operating procedure for your experiment? If you have one, you're super lucky. You don't have to do anything. You just follow the procedure. If you don't have one, next thing you do, okay, somebody had done this before. It must be that somebody somewhere on the planet had looked at separating carotenoids, right? So you go and look at published works. But here's a word of wisdom. Often, over 90% of the time, you get a method, try to repeat it, doesn't work. It worked for that particular researcher with whatever equipment they have in their lab, with their column, with their stationary phases, with the mobile phase, but you try to replicate it, it doesn't work. It needs some tweaking, and that's where you come in. Okay, so I need to tweak published methods. Very rarely you have to establish anything from scratch. People have been working with chromatography before I was born. So there's a lot of literature. So, but you have a starting point. And then, like I said, never works. So you have to make it better. You get a procedure and then you start thinking about your sample. So that's the next step. What do I know about the samples that I want to separate and identify? Carotenoids, what do I know about them? What's their polarity? What if they absorb light? Do they absorb light at what nanometer wavelength? So what do I know about the sample is the first question you want to ask yourself. Well, second, how many components need to be resolved? What do I know about the components in my sample? Do I have 3 types of carotenoids? Do I have 1 type? Do I have 5? How many? How close in characteristics they are? If they're very close in their characteristics, the separation can be very tricky. So you need to gather this information. And you have a lot of resources to gather this information. Again, you have to do your homework and do some searching. And then what degree of resolution do I need? Do I need them really well separated from each other? Or is it okay if they are not separated because I just want to qualitatively determine their presence? If I just want to know if A and B are present, if I see 2 peaks, they're present, A and B are present. But do I need to quantitate? You cannot quantitate these accurately without well separation. So that ties into, is it a qualitative, is it quantitative? What are you really after in your objective? So you have to gather information, ask the right question, and try to get to the right answers. So once you know, you've read, you've gathered information, then you want to choose a chromatograph separation mode. So this is a figure in your chapter in the book. It illustrates how many options you have based on the characteristics you know about your product, your components that you want to separate. And oftentimes, you have multiple options, option 1, 2, and 3. You can either use reverse phase chromatography for the same sample. You can use ion pair. We're going to talk about ion pair next week. So if you have charged molecules, you add an agent that neutralizes the charge, so you can use reverse phase chromatography. That's basically what ion pair is. And then ion exchange. if you're having a charged population. So you look and say, okay, I have three options. How do I choose? How would you choose? What would make you go with option 1, 2, or 3? Huh? Yeah, well, the characteristics of it's an ionic species, so you can either do this or that, let's say. Yes, Ben? Well, yes, simple as that. What do I have in my lab? What am I more comfortable working with? What standard operating procedures I have already developed in the lab that will help me? What's my personal preference? And go from there. So you choose your mode of separation, and then, you chose, but there are multiple stationary phases and multiple mobile phases that you can choose from for the same application. So again, you start thinking about where should I start? What stationary phase? Again, looking at references can help you. You will pick a couple based on the references and try there. You start there. And then you would decide on the elution mode. Is it isocratic, meaning the mobile phase does not change in concentration or temperature or flow rate during the run. Nothing changes, so it's isocratic. Or is it gradient? There is something called continuous or stepwise, meaning continuous, like you're always increasing the concentration of acetonitrile over time in a constant manner. So constant increase in acetonitrile, for example, over time. But sometimes you have stepwise. So you go, let me illustrate what stepwise means. You'll see it, you'll give examples next week as well. But stepwise means you start isocratic, like time 0, 10 minutes, same concentration of the mobile phase, and then you have continuous increase in 5 minutes. So you increased your acetonitrile concentration continuously over 5 minutes, and then you have the same concentration, you go up, same, and then down again. So stepwise. And I'll give you examples next week as when is this valuable and why. Okay. And then flow rate. So is it 1 milliliter per minute, or is it 0.8 milliliter per minute, or 1.2 milliliter per minute? Sometimes you have to find the optimum flow rate to get the optimum resolution. And I'll talk about the role of flow rate in resolution later on. So it does affect how well your samples separate. Okay, temperature. Like in the video for HPLC specifically, the column is housed in an oven, and you regulate the temperature of that oven. And when you increase the temperature slightly, the mobile phase becomes less viscous, and the transfer of solute becomes faster, easier to move in and out of the stationary phase into the mobile phase. You get equilibrium faster, so your analysis time is shorter, and your separation is better. So temperature and flow rate are really important parameters that you can work with to enhance separation. We'll talk more about that as well. Okay, so you have to think of all of this. Oftentimes when you don't have a clue, you start with isocratic, the easiest, and see what the run looks like, how long it takes to get separation. And from there, you look into continuous, stepwise, how do you adjust the flow rate, how do you adjust the temperature. So you start simple and add complexity to improve your separation. Okay, so now we're going to talk about resolution in general, which is separation of the two or more peaks. But before that, there are certain terms. You're going to hear a lot these terms in chromatography. Some of you might be familiar with these terms, others, a refresher again, others have not heard of them. Okay, so there is something called retention volume associated with the retention time. So the volume of the mobile phase it took for the peak to come out. So from the moment of injection to the moment where you saw your peak, and usually we record at the top of the peak is where we record the volume it took to get here, from the beginning of the injection to this. But oftentimes, instead of reporting volume, you report retention time. So how long it took from injection to elution. It's retention time, or the time that molecule or compound stayed on the stationary phase. That's why it's retention. Okay? So there is also T prime here, which is an adjusted retention time, because you have something like is called the void volume. We talked about that last time. The volume that from injection to here, nothing is coming out, supposedly. You don't want anything to come out here. It's the entire volume of the column that is not related to the interspatial volume within the particles of your stationary phase. So it's the volume of the column, basically. One volume of the column. Depending on the size of your column, the length, the dimension, this could vary. Okay? Each column will have its own void volume. Okay. So adjusting the retention time based on the time of the void volume, we call it solvent front. This is the solvent front. So this is a very common term, that this peak is your solvent front. Okay, so adjusting this gives us a better estimation or comparison if we're trying to compare retention time, let's say, with the published work. If we take out this time here, you have better comparison. Why is that? Because tubing sizes differ. So you have your column, you have a tube that connects the column to the pump, to the injector, connects the column to the detector. So there are different sizes of the tubing parameters and length. So that will affect also your solvent front. So by adjusting that, you take into account the differences in instruments in terms of void volume. Okay. That's the adjusted. Here I'm saying if two compounds co-elute, you need a further separation using another technique. Sometimes you start when you're preparing or purifying compounds, you start, let's say, with size exclusion. You want to say, I'm going to collect everything that is 10 kilodalton. Okay. Two things can be 10 kilodalton, but they can be very different. So you use another chromatographic technique to separate them based on charge, based on their polarity. So oftentimes one peak does not mean one compound. Okay. Okay. Identification of peaks, that is based on something called separation factor. The separation factor, or alpha, is the relative retention time of peak 2 to peak 1. The higher the alpha, the better is the separation. Okay? This means like the longer the distance between this and this in terms of time, you will have better separation. Alpha gets smaller when these two peaks lose resolution. That means when they come closer, they're not separating. They approach 1. Basically, this value will approach 1. If T prime R equal T prime R2 equals T prime R1, then alpha is 1. Alpha is 1, you don't have separation. Alpha greater than 1, then you start getting separation. Okay. Questions? Yes?
Can you repeat the category? Why is one peak associated with just one compound?
Yes, very good. So one peak, usually you will only see one peak sometimes, but then it might be two compounds, because if you're doing size exclusion, two compounds might have the same molecular weight. There are multiple compounds that will have the same molecular weight. So its molecular is not really a species specific. So you will have two, then they will only show up as one because they have the same molecular weight.
So, but you're not saying that one compound will come up as two?
No, no, no. Two compounds might come up as one. Oh, there are instances when one compound can show up as two if they are isomers. Or if one is ionized, one is not ionized. Like one is carrying a proton, the other one is not carrying a proton. One is an enantiomer to another. We'll talk about all these examples as we go along with the semester-long chapters. But good question. Any other questions? Okay, good. So now that we understand some terms about retention, let's talk a little bit more, introduce more terms. The first term I want to introduce is the width. So the peak, it has a height and it has a width here. Okay? And sometimes you have the total height, other times there's the midpoint in height and the midpoint in width as well, because they can be integrated into the equation. So the width of the peak indicates how well or efficient your column is or efficient your separation is. The wider the peak, the lower the resolution. Learn that for now, and we'll talk about what causes the peak to be wider, what causes the peak to be narrower. Okay? If you have too wide peak, they're going to co-elute. The narrower the peak, even if the retention time is very close to each other, but they're very narrow, sharp peaks. So you might have 1 minute. You have here, let's say you're reading absorbance, and then you have time. And you might have here 1 minute, here 2 minutes. They're very close to each other. But if you have really sharp peaks, they're going to separate. However, if you have broad peaks, they're not going to separate. Both of these have same retention time, but they didn't separate. So the sharper the peak, the better is the separation. All right, so this explains this equation right here. Resolution equals 2 times the difference in retention time. Delta T is the difference of retention time of peak 2 and peak 1 over the width of peak 2 and peak 1. Again, so if we want to apply a mathematical equation, if this value is large, resolution will be low. Okay? If the difference in time is large, the resolution will be high. Okay? So, and I will introduce one concept and we will stop. We will pick up next Monday. Resolution is a function of 3 separate factors. So 3 factors affect the resolution or the separation of 2 peaks or more peaks. You have column efficiency, the selectivity of your column or stationary phase, and the capacity. Okay? Efficiency, we'll talk about that, how efficient is the column in terms of time and separation of the peaks. Selectivity is how selective is your stationary phase to the different components. If you have 2 components that are very close in partition coefficient or distribution coefficient, how selective is this column to make them separate from each other? Capacity, how many functional groups you have on the column. Okay? The more functional groups you have, the higher the capacity of the column. And over time, you're going to lose efficiency, you're going to lose selectivity, and you lose capacity. The longer you use the column, you're going to lose on all of these. Resolution will be poor. You cannot use the same column forever because of these factors. Okay, so we can stop here, but Wednesday lab, please stay and come talk to me for your groups. Have a great weekend.